Thank you very much for your introduction. It's very nice to give my talk at Mobile 2 Auditorium because I have been working on Hamiltonian systems so many times. And in my preceding paper, two types of geodesics are studied. One is mixture geodesics, and the other is Riemannian geodesics. And as for exponential geodesics, I have already studied in which is presented in my discussion paper. So my talk is organized as this slide shows. So due to limited time, I would like to focus my talk on the confinement of the mixture geodesics in the statistical model of the finite set with an element. First of the ODE description on the phase space of it means the cotangent bundle of the statistical model is obtained for the M geodesics. And by solving the ODE by quadrature, a non-clear account is found for the confinement of the M geodesics in the statistical model. Further, a strong support to the confinement is given by the simplex deduction to the phase space. Okay, Riemannian geodesic will be mentioned very little if time remains. So this is a main theorem in this talk. It is presented as the theorem 4 in my preceding papers. The mixture geodesics is described in the form of this equation 31. Please keep in mind that the numbering of the equation in this talk are the same as my preceding paper. This ensures the confinement of M geodesics, and furthermore, it's integrable and have a sufficient number of conservative quantities. So in this statement, you may wonder that what does confinement mean? I'll give you the overview in the two-dimensional case. In the two-dimensional case, the statistical manifold, statistical model we are concerning is expressed as a two-dimensional standard simplex with a coordinate c. So in literature, we are told that the mixture coordinates, mixture geodesics, are straight lines on the simplex. But so it's expressed in this form. So the M geodesic may extend out of simplex. It's a bit embarrassing. And at the same time, I'm a bit afraid that it's only I who does know the account. Okay. So the question arises, a pair of questions arises. Can the M geodesics be confined in the simplex? If so, how? In this talk, a non-clear account is given. So to give the account, we are going to prepare the phase space of the statistical model, namely the cotangent bundle of simplex. So let me start with a statistical model of the finite set. It is realized as an n-1 dimensional simplex of this form as equation 1. And C is, of course, a bicentric coordinate system, which will be applied in this talk throughout. As a characteristic of information geometry, the simplex is endowed with a Fisher metric associated with the finite element distribution. Oh, sorry. At the same time, C in this case is understood to be a mixture coordinate of the statistical model. It means that in terms of C, the mixture coordinate is expressed just as the straight lines on the simplex. So again, question is of this talk is can be confined, and if so, how? To accomplish this question, cotangent bundle has to be introduced in the following. So we start with a tangent bundle, which takes a bit simpler form than the cotangent bundle, and using the isomorphism associated with the Fisher metric, it is expressed in equation 5. The cotangent bundle is expressed in the form of equation 6. The cotangent bundle is endowed with the standard symplectic form omega in this case. So I'll skip this slide very shortly, but so you know, so many constraints appeared in through a preparation of the cotangent bundle, and we can skip these constraints if we apply the symplectic reduction later. So we are going to move to mixture geodesics on the simplex. So let us start with a very naive observation of the straight line on the simplex. Of course, it is written in the form of equation 25. And as t tends increases, it would be out of the simplex. And so without any additional account. So to avoid this, we are going to switch from the tangent vector distribution to the cotangent vector distribution. It is realized by the isomorphism of tangent bundle to the cotangent bundle. It is given in equation 5. It can be rewritten in the form of the equation 26 of this form. Then, from the 29 expression, we have the equation that the xi dot must satisfy. And the next question is how must eta dot of the M geodesic can be described. The equation on eta must be compatible with several conditions. One is the conservation law. As the second one is evidently geodesic equation for the M geodesic. And finally, it's constraints to describe the cotangent bundle. So as a result, we have equation on eta of this form. And finally, leads to the first order equation on the phase space for the M geodesics, just like in the equation 31. Of course, it is very easy to solve. And the solution is on this form. As you can see, for C, we have nothing new, the conventional distribution. However, if you look at eta j, there is at least one component divergent at a finite time. It really exists, and I will show you some illustrative example of this form. It shows a solution curve with initial condition of this form. As you can see, if the time tends to the 1 second, C3 tends to the boundary, and while the eta 3 diverge. So on the simplex, the same solution is, of course, shows a straight line with tending to the boundary at a finite time with a divergent moment. So generalizing this situation, equation 32 and 33 imply certain component tending to the position variable to 0 and the divergent momentum. So it shows the continuity breakdown on the straight line. So we must stop at the finite time. We are thinking of the finite time solution. Okay. So this observation, it's a new, I think it's a new clear count for the confinement, and it is strongly supported by if we apply the symplectic reduction to our analysis. The reduction is accomplished from the cotangent bundle of the n-dimensional positive Olsen to the phase space we are thinking of. It is we will call it the cotangent bundle positive Olsen as a higher dimensional phase space. On the higher dimensional phase space, we can think of the symplectic R action associated with the momentum map J of this form. Then, following the Marsden and Weinstein's reduction scheme, the reduction is accomplished along with the reduction diagram shown in the equation 14. So as a result, the reduced reduced symplectic manifold, it is a quotient manifold of the level set of J by R action. It is symplectomorphic with our phase space. So, of course, the reduction simplex form is reduced together. So, it is summarized in the theorem 1 in the paper. And the next question is, what first ODE does come out that is reduced to the ODE for the M geodesic? As an equation we are thinking, we have the ordinary differential equation of the as a form of equation 34, which of course reduced to the ODE of the M geodesic. And we are going to solve this equation 34 too. On the restrict on the level set, the solution of this equation takes this form. Of course, the similar like the M geodesic case, we can observe at least one divergent momentum. But what is more important is the existence of a square root solution. It really vanishes if t exceeds limited time t sub m. Okay, it is due to the square root existence of a square root, and at that time, together with the banishment, associate momentum diverges to minus infinity in this case. And one of the graphical example is can be drawn like this. It corresponds to the my previous illustration. The initial condition correspond together. So it starts with this point to move to the tends to this point marked by star. At this point, the solution stops, vanish anymore. Okay. So in summarize, of course, the equation 35 can be reduced to the 32. It's a M geodesic solution, and vice versa. Okay. So since xj, one of xj vanish, at the same time, the corresponding XCL vanish together. So it is fortifies our confinement account in the very rigorous way. We have more on mixture geodesics ODE on the phase space. One is commutative quantity are found. Of course, it's a it is understood to be a tangent vector along the M geodesic. And the other one is, what's very interesting is that the equation is non-Hamiltonian. Even in a locally, it's not even locally Hamiltonian. So these results can be summarized as in the theorem 4. It's the main theorem in this talk. The non-Hamiltonian equation 31 on the phase space describes the mixture geodesic, which ensures the confinement of the M geodesics in the statistical model. And it is integrable, and also allows to exist sufficient number of commutative conserved quantities. So I will skip the Riemannian geodesics in this case. So how many? 5? Okay. So now I'm going to the summary of this talk, concluding remarks. We find the first order ODE on the mixed geodesics on the statistical model in this talk. And together with the equation, a numerically account for the confinement of the mixed geodesic is found. To fortify our result, the symplectic reaction works very well. Other important characteristic, for example, Hamiltonian property, integrability, and extendability to the time scale is shown in this table. So, final remarks. As a final remark, quantum analog of this theory is now in progress, and in exponential case, the quantum case is already exists in the discussion paper. So, thank you very much for your attention.
Thank you very much for a very nice talk. Now it's time for questions.
Can you tell something about the quantum analog you were mentioning at the end of your talk? Can you say something about the quantum analog?
Oh, yes. Quantum analog is only made by the, yes, okay. So now we have, for example, already the equation. So it's a Riemannian. Equation 31, yeah, it is. In the classical sense. So we are going to replace it in a quantum case. This equation appears in the diagonal components. So we are going to extend it to the Hermitian unit trace, a positive Hermitian unit trace case. Of course, we are fighting with some kind of a non-commutativity and to construct a product. But I think it will be okay.
Other questions or comments? Then maybe I have some questions. So this theorem 4 is actually seems very subtle because it's non-Hamilton, but you have many.
Yeah.
It's integrable and you have conservative quantities. I think something like a maximal number of conservative quantities. Right. Could you explain why it could be just non-Hamiltonian, whereas it's integrable?
It's in this case I'm going to say about the integrability simply by quadrature.
By quadrature, okay.
Not in the review sense.
Okay, I see. Thank you. Maybe one more comment or question?
Maybe I have a question. No, I can just say that. So I wonder what is the motivation for the confinement of this geodesics in this space?
Oh, thank you very much. This is my personal question. Why it is not allowed to the outside? If no account, the straight line goes out to the simplex. So my question is that is there any trick or reason it is confined or not? Very simple one.
Is it okay? So it seems that this confinement is actually first explained just by using the Hamiltonian framework. Right.
Maybe it's the phase space construction is key.
I see. So one has to go up to the tangent band, cotangent band.
Tangent band formulation is not so successful.
Okay. I see. Thank you, and I think it's time for then let us thank the speaker again.
Thank you.